When we talk about computers, memory is everything. Every single program you've ever run, every game you've ever played, and even this video you're watching right now, all of it lives inside computer memory at some point. But here's the catch. Computers don't think in sentences, images, or music. They think in numbers. And those numbers are stored and managed in a way that might surprise you. At the heart of memory management are bits and bytes. You already know a bit is the smallest unit of data, either a 0 or a 1. A byte is just 8 of those bits grouped together, and in theory you could manage memory entirely in binary, just a long, endless stream of ones and zeros. But that's insanely hard for humans to read or debug. Imagine scrolling through pages of binary just to find the location of a bug in your code. That's where hexadecimal steps in. Hexadecimal, or base 16, is like the shortcut language for programmers. Instead of writing long binary strings, hex condenses them into a form that's way easier for us to understand. For example, the binary string 11111111 becomes just FF in hex. Same information, way more compact. And when you're working with memory addresses, compactness isn't just convenient, it's absolutely necessary. Think of your computer's memory like an enormous hotel. Every room in that hotel has a unique address, and each address stores something, a number, a character, a part of an image, or even an instruction for your program. Now imagine if every room number was written in binary. A single address could look like 101011010101101. That's a nightmare to keep track of. But in hex, that same address might just be 0xAD75. Much easier to read, much easier to manage. This is why hex is the universal tool of programmers when it comes to debugging memory. When your program crashes or you're tracking down a bug, you'll often see an error message that looks like segmentation fault at 0x040FF1C. That's a memory address written in hexadecimal. It tells you exactly which room in the hotel your program tried to access incorrectly. Without hex, debugging would be like searching for a needle in a field of identical haystacks, and it doesn't stop there. Hex is also used to represent the contents of memory itself. Open up a hex editor and you'll see raw memory displayed as hex values, numbers and letters neatly organized in rows and columns. Each two-digit hex number corresponds to 1 byte in memory. It's like looking at the DNA of your program. With hex, you can literally peek under the hood of your computer and see the raw structure of everything running on it. Let's make this practical. Take video games. When a character moves across the screen, every position, every texture, every action is stored in memory. Game developers use hex to debug glitches, locate assets, and optimize performance. Or think about web browsers. When a website loads, the images, text, and scripts all get stored temporarily in memory. If something goes wrong, engineers can use hex to pinpoint exactly where in memory the error happened. Here's another way to look at it. Imagine you're editing a massive book with millions of words, but every word is stored by its page and line number. Binary would be like writing out every page and line in long strings of ones and zeros. Hex is like a clean, compact numbering system that lets you jump to the exact page and line instantly. It's the difference between getting lost in the weeds and having a clear map of the territory.
So why do programmers still rely on hex today when we have high-level languages and powerful tools? Because at the deepest level, computers still run on binary, and hex is the perfect bridge between raw machine data and human readability. It's the Rosetta Stone that translates between the machine's raw reality and our ability to make sense of it. In short, bits and bytes are the raw material, memory management is the system that organizes it, and hexadecimal is the lens that makes it all visible and manageable. Without hex, programmers would be flying blind. With it, they can see the structure of memory, track down errors, and optimize systems that power everything from tiny apps to massive operating systems. And this is just scratching the surface. In the next video, we'll explore how memory isn't just about storage, but about access speed, efficiency, and the hidden hierarchy of caches, RAM, and virtual memory. That's when you'll see how computers juggle memory to keep everything running smoothly. So if you want to go deeper, make sure to hit like, subscribe, and stick around. because understanding memory is one of the most important steps in truly understanding how computers think.